Good morning, everyone. Welcome to the new Guru class of today. We already have reached the time. However, we would want to wait for a little more minutes, maybe a couple of minutes, as we're expecting more people. Kindly bear with us, and we shall start the session soon. Thank you. Good morning. I am back again. Thank you so very much for being patient. First of all, I would like to wish you all a very happy new year. I know this is our first meet post New Year, and I really wish this New Year brings a lot of success in everybody's life, right? So we will start with our session very soon, right? Before before we proceed, I would just like to give you a little brief about Unikaksha. So basically, we are an online education providing platform that helps students and working professional, from IT or non-IT background to upskill themselves in their tech career with the help of our top mentors and industry vetted curriculum. So far, we have had a positive impact in the careers of more than 5,000 students. And today, with this Guru class, we really hope to help you in the same manner. Right. So today's topic would be utilizing the power of graphs to solve a real world problem. I would also like to introduce our experienced mentor who is going to take you through this topic. So today the topic is going to be covered by Swati Yadav, who have overall 8 years plus of experience in Java full stack development, web development. She has 2 years of experience as a certified trainer in Java, Web, Python, data science. She has handled classroom deliveries and curriculum development for K-12 segment for Web and Python and Java FSD curriculum development as well. She's also working as a trainer, and she's a working professional who have been in this training profession since a very long time. So very warm welcome to Swati. Swati, over to you for today's session.
Hi everyone, good morning. So it's actually very chilly out here right now. Yeah, I hope you guys all are in areas where it's warm. So now starting with our session, as I've already been introduced, I don't think that you need another introduction from me. Before we, delve into the real world, problems of graphs, I wanted to have a quick overview of what exactly graphs is. And, the graph is a versatile, data structure with many variants. It's not just one data structure. There are so many different types of graphs that we have, and you can solve, or you can use it to solve problems. And and it's not just limited to the interview tasks only that you get. So it's actually very useful. So in any effective programmer, you see, they need a solid understanding of data structures, and not only in data structures alone, but there is a specific topic which is graphs. Okay. So technical interviews will often, they are going to test your problem solving and critical thinking skills, which are entirely, based on DSA. And graphs are one of the many, important data structures in programming. And in most cases, understanding graphs and solving graph-based problems, that does not come easy, to be very honest. It requires a lot of practice as well as an open mind to have that kind of learning. And if you look closer, I would say, the whole wide world, the whole universe could be a graph in itself. So we can think of universe at the very start, as a collection of abstract relations between abstract elements. So that is also kind of a graph. So you see how graphs, they fit into our world, into the universe itself. So it's not just limiting to that you have to, just the graph theory, just the graphs in data structure, but it is actually in use out there. So data structures, are, as you might be aware, that these are specialized formats that we use to store, process, and retrieve data according to our needs, right? You might have done data structures before, you might be aware. The simplest of the data structure that you might be aware of is arrays. You might know stacks, queues. You might have implemented stack and queues using arrays. Recursion. It's a kind of in a method of to implement. Then different algorithms. All of this, these data structures, linked lists, graphs, trees, spanning trees. All of these, they are a way for us to store, process, and retrieve data, according to the needs of the organization or according to the need of the process where you are applying it. So there are several data structures that serve different purpose based on the requirements. Like, for example, you have different type of utensils in the kitchen. Yes. And each one of them have a different, purpose to serve. In one, you're going to make tea, one can be used for Maggie and, whatnot. So for example, we use bowls or cups, right? We have bowls, we have cups for storing liquid items, whereas plates won't do that, plates only for serving, right? So similarly, in some cases here in data structure, you need an array data structure. In some case, you might need a linked list where array is not of use. And in some certain cases, you will be needing graphs. So before we zone in on the graph data structure, you should be aware of certain things, that what basically DSA and, if this is your first time getting to know, graph data structure, I would always suggest you that you should have a background of it, that, you should be aware of data structures and algorithms, arrays, what is an array, stack, queue data structure, types of different queues, linked lists, all those things that you need to be aware of. Now, moving to introduction, so to the graph itself. Now, what is a graph? What is a graph? Any one of you who can relate, who already knows about it and can put it in the Q&A. So you have Q&A open. You can, always reach out, put your questions over there, for us to pick it up and talk to you guys. So a graph, it's a non-linear data structure. Okay, it's a non-linear data structure. It's a collection of nodes which are connected to each other by edges. So I'm going to take you to a new screen share, just a moment. Graph is a non-linear data structure, okay? There are, it's a collection of nodes which are connected to each other by edges. Now, what are nodes? What are edges? You might be wondering, wait, what is this? Tell me, na? Anyone who knows what are nodes and what are edges? So vertices in a graph, vertices in a graph, the vertices like A, B, C, D, those are called, sometimes referred to as nodes. And edges, those are the lines or, the arcs that, connect any two nodes in the graph. So formally, you could say a graph is, composed of, a graph is composed of a set of vertices and edges. Basic definition. So if I have to tell you, if I have to write over here, how to represent a graph. Now, if you ever see that, what a particular graph is, so basic could be okay. Now these are vertices or nodes. Okay. There are lines which are connecting these vertices together. Let's say like this. And these are your edges. Okay. A simple representation of a graph. Okay. So this is what a particular graph, this is a very basic graph that you see. It's not a complicated structure, but yes, it's a representation of a graph. There are different kinds of graph that you can make, the same one, you can have another kind of graph. So all of them, if there are nodes and edges connecting them, that is a graph. Let's say 4, 6, 5. These could be directed, these could be undirected. Undirected means you're not specifying any direction to the edges, okay? Now these are also nodes. These are nodes. This is node. This is node. This is node. And this is an edge connecting those two nodes together. That is an edge. Okay. So there are no rules to it that you have to call it nodes or vertices or edges or arcs. Whatever suits you, you're going to call it that. Okay. So the basic terminology. Now, let's understand this with an example, right? Let's take an example over here and let's try and understand it. We'll come to that, right? So let's try and understand it with an example. So on Facebook, right, every profile that we see is a node. Okay, on Facebook, we see every profile is a node, including the photos, the videos, we have events, pages, and all other properties that have data. And every connection, it acts as an edge, whether it's between you and your Facebook friend or just a page that you've liked. So Facebook, this is an example where you will find graph. Again, relate. This is a real life example. Social networking sites, just like your Facebook. Okay. That means every profile is a node. All the photos, videos, events, pages, all the other properties that have data over there, those are the nodes. Every connection, acts as an edge. Whether, you talk about you and your Facebook friend, that's an edge. Or any Facebook page that you've liked, any other video that you've liked, that's an edge from one node to other node. Okay. Facebook and other social networks are just huge collection of nodes and edges. So that is one real life example of, where you find graphs in the real life scenarios. Now, graph data structure, they solve many, problems. Most importantly, they are used to represent networks. Okay. For example, the network could be you could say, road network, in any city, or, the circuits that we have, the road, the whole entire city map, you could say. That is also a graph, connecting one point to other point. The airline systems that we have, the whole map, to take a flight from point A to point B, that is also based on a graph structure or on graph theory. So again, one thing to remember is that a graph, it contains a collection of nodes, which are also called as vertices. Now, a collection of edges connecting the vertices, okay, that is represented as an ordered pair. Okay, so you could say one edge. That could be, let's say you have a point A to B. This is your ordered pair. From where are you going? Fine. So vertices, edges, and the graph itself. Now, if I give you an example, yes, it is map, city map, road maps, road views. Those are the graph structures, right? Now, if I give you an example, let's give you an example, and you tell me what are the vertices, what are the edges which are formed over there. It's a very simple one. 0, 1, 2, 3. I'll tell you that these are vertex and this is an edge. Now tell me, how many vertices are there? You have to make a set of it, right? We have 0, 1, 2, 3. These are the vertices. Let's see the ordered pair of the edges that we have. Let's make the edges, right? So how many pairs can we have over here? From 0 to 1, one edge. From 0 to 3, another edge. From 1 to 2, and from 2 to 1 to 2 and 2 to 3. Right? These are your edges. Now to represent a graph, you write G. This is the representation that a graph is a collection or is a set of vertices and edges. The basic terminology we've already discussed. We know what's a vertex. We know what's an edge is, right? So edges in your graph, it's just what the lines, that connect two vertices together. Over here, as you can see, like 0 and 1, they are connected with this particular line. So this is our edge, and so on. Now, edges, they can be represented in form of, dimensional arrays, multi-dimensional arrays, 2D arrays. So another thing, or the representation of graphs, it involves representation of graphs. Okay. So one is your adjacency and another is paths. Two more terms to look for is and paths. Now, adjacency that we see is a vertex you say is adjacent to another vertex if there is an edge connecting them. Like just in this particular image, these are adjacent, right? There is an edge connecting them. These are adjacent, there is an edge connecting them. So adjacency just means that a vertex is said to be adjacent to another vertex if there is an edge connecting them. That is your adjacency. Now, what is path? You in data in this kind of data structure, you will see that your this particular graph, there is a term which comes as path. Now, a series of edges that take you from one vertex to another when they are not adjacent to each other, that is called as a path. Like here in the same example, you want to go from 1 to 3. Okay, 1 to 3 you want to go. So these two vertices, these two nodes, they are not adjacent to each other and you have to go through some other vertices as well. So how can you go over here from 1 to 3? What will be the path? You can take this path and this would be 1, 2 and 2, 3. So this is a path, So a series of edges that take you from one vertex to another when they are not adjacent to each other. That is your path, okay? One more thing that you need to know is I took a term which is called as directed graph. If you remember, just now said that there are directed and undirected graphs. Now, what do we understand by directed graph? The same example, directed means that you can go from this vertex to this vertex if you specify that this is the only path, like this, that I can only go from 0 to 1, but there is no way back. From 1 to 0, it's not an edge. Here that you see in this particular example, this is not directed. You can go from 0 to 1 or 1 to 0. Okay? Here I have told explicitly that this is the only path. You can go from 0 to 1 only. You cannot come back. Okay? That is your directed. So a graph in which an edge doesn't necessarily means that there is an edge, a reversal of it. Let's say you go from 0 to 1, fine, but there is no edge from 1 to 0. So an edge in a directed graph, it travels in one direction only. Okay. And to represent that it's a directed graph, you make use of arrows. Fine. So there you make use of arrows. Now the thing which I wanted to take on is the representation of graph. Graph and its representation. How do you represent the graph? We are already aware, right, of a few things like that, a few components maybe. The two components of any graph are two components. And what are those? A finite set of vertices, they are called nodes, and a finite set of ordered pair to form the UV pairs, those are called as edges, right? Now, the next thing is how to, kind of represent any graph in any format. So let's take an example, like you have 0, 1, let's go 2, 3, and 4. I say I can go from here till here, then from here. These are the edges, okay, from where I can go. This is not a directed one right now. a simple graph that we have right away in front of us. This is an undirected graph of 5 vertices starting from 0 going till 4. Okay. Now there are two most commonly used methods. I'm not saying these are the only two methods, but most commonly are adjacency matrix and adjacency list. Okay. Adjacency matrix and adjacency list. There are other representations also. There is an Indian incidence matrix that you have, or the incidence list that you have. But these two are the most commonly used. They are kind of more practical, you could say, that has in been used. Now, what is an adjacency matrix? With the term matrix, we know it's something like you build a 2D kind of structure for it. So obviously, with the name that it suggests, there has to be a matrix structure, table, rows, and tables. Right? So adjacency matrix is a 2D array. It's a 2D array where the size is your V by V. That means V is your vertices, number of vertices. You have 4 vertices, then the size of the matrix would be 4 by 4. You have 5 vertices, 5 size would be 5 by 5, and so on. So adjacency matrix is a 2D array of size V by V, where V is the number of vertices in your graph. Okay. Now, we take a 2D array, let's say ARR over here. It's implemented through arrays. Okay. We take a 2D array, and then what do we do is that here in this array, any slot where you have 1, where you have given 1, let's say, that means there exists an edge from that vertex to the another vertex. Okay, let's say this is I and this is J. So if it has 1, that means there exists a path, edge. Okay, there exists an edge between those two vertices. Okay, if there is no path, that will be indicated as 0. Okay, this is also used to represent the weighted graphs. Weighted means where there is some weights. Weights means you have some weights over these. It's all something that comes handy afterwards, and then you have the shortest path and things of those kinds of, algorithms which you implement with that weighted graphs. But right now, to understand 1 and 0 in an adjacency matrix, it just means that there exists a path. If there is no path between the two vertex, it will be denoted as 0 for that particular cell. Okay. Now the same example, if I take the same example and I want to make an adjacency matrix out of it, it would be 0, 1, 2, 3, 4, 5, and again 0, 1, 2, 3, 4, 5. So you will see how many it is. Not 5, yeah. 5 is not there. I'm so sorry. Till 4. So your whole matrix is this. Okay. So these are like 5 vertices, right? So it would be 5 into 5. 25 columns. 25 cells. 1, 2, 3, 4, 5, and 5. Right? 25. Now you have to fill up your adjacency matrix. Now it only means that if there is an edge, there will be 1. If there is no edge, there will be no 1. Starting from 0 to 0. Is there any edge for 0 to 0? If there was an edge, it has to be like this, but there is no edge. So nothing like this. Okay. So there isn't any edge over here. No, it's not an edge. Going from 0 to 1, yes, there exists an edge. From 0 to 2, no. From 0 to 3, not again. And 0 to 4, there exists an edge over here. So that would be 1. So you have to fill your matrix in terms of zeros and ones. There is an edge, you put 1. There is no edge, you put 0. The same thing next time. 1 to 0, yes. 1 to 2, yes again. Sorry, 1 to 1 is no. And 1 to 2 is yes. And 1 to 3 again, yes. 1 to 4, yes. Okay? So this is how you are going to fill it up. 0, 1, 0. 2, 2, 2, 3, yes. 2, 4, no. Okay? 0. Then 0 again. 1, 1, 0, and 1. The last one is 0 to 0, 4 to 0, yes. 4 to 1, again, yes. 4 to 2, no. 4 to 3, yes. And 4 to 4, 0. So this is your adjacency matrix. This is the representation, graph representation in terms of adjacency matrix. Okay. So representation is easier to implement and follow. Removing an edge, it will take a time of O1. Okay. This is the worst case, which is 1. And like whether there is an edge from vertex, A to vertex B, those efficiencies can be done in O1 time. Okay. But the only problem that comes with adjacency matrix is it takes a lot of time. A lot of storage. Why? V into V. Okay. Even if the graph is sparse, even if the graph is sparse over there, that means it contains less number of edges. Okay. Even, it has less number of edges over there. It is going to consume the same space because it has to accommodate V into V edges over there. And it has to compute all the neighboring, you could say all the neighbors of a vertex. Okay. So all the neighbors has to be computed there. It takes a time of OV, which is again not efficient. So this is one example of adjacency matrix and how to implement that. If you have to take a look at the algorithm of it is pretty simple. You don't have to do much into it. You will just be running a for loop. Okay. So there is a loop that you'll run. Let's say it's from 0 till M. Okay, that we run. Now, N and M. What are those? N is the number of vertices. And M is the number of edges. Okay. And then you are going to have, first you're going to take another array, let's say R, and it will be of size N plus 1 for both. Okay. That it will go. The number of number of elements that it can go inside it. You are going to run a loop that I said, this particular loop from 0 till M. From the number of edges, how many edges you have. Take the inputs for U and V, the vertices, and simply where you have an edge from U to V, give 1. Where you don't have an edge, you are going to just place 0 over there. That is the only thing. Okay. So if you have an edge from U to V or V to U, give 1. This is the only implementation of your adjacency. And afterwards, what you have to do is, you simply has to print it out. Like the way we print, run a for loop to print the matrix. That is what we have to do. The next kind of representation that you have is of adjacency list. Adjacency list. So an array of list is used over here to implement adjacency list. The size of the array over here will be equal to the number of vertices. Number of vertices. Okay. So an entry of, you could say, ARR of I, it represents the list of the vertices which are adjacent to this particular ith vertex. So this representation, it can also be used to represent a weighted graph again. So both of the methods, either your adjacency matrix or adjacency list, they can represent the weighted graph. The weight of the edges that can be represented as a list of pairs. Okay. Now, to look at a simple representation of it, let's see. You have the representation somewhat looks like this: 0, 1, 2, 3, 4. This thing is going to, if there is, a vertex, it's going to hold that vertex. It's a particular list, and the address of it, if you've done kind of like a linked list structure, you'll know that it holds an address for the next vertex. Okay. That's it. If for the next element, it's going to hold the U, the vertex, then the address of the next vertex, and that is going to point to that. If there is another edge from it, it's going to hold that as well. Okay, something like this. From the next, the next element will have the vertex and the address for the next one pointing to the vertex. And so on. Okay, let's save the graph that we have 1, 4, and go to 2. And from fourth one, you can go to 3, even on the value for 4 and 1. The representation of your adjacency list, it looks like that, We use dynamic arrays here, or you could say in Java, we use array list to implement this adjacency list instead of the linked list. Okay. So we don't use linked list. In Java, we use array list for this. If you're aware of Java, you have a collection called array list. Okay. In our the JavaScript, you simply just use the arrays to implement it. You create an function for adding the edge over there. So you have to add an edge, so that edge will, or it's an utility function that we create to add a edge in any undirected graph. So you give the array, you give the vertex into it, and you simply just push into the array itself. Okay. That is what we do for the implementation of it. That is your representation, graph representation. The next thing that you need to know about, just give me a moment. There is a poll which is coming for you guys now. Okay. So I would like to give you a question.
So we'll just have a quick attention check here. There's the first poll on the screen right now for you. So here goes the question. A graph consists of vertices and nodes, vertices and edges, nodes and pairs, pairs and edges. Let's see who gets this one correct. And I think that will give us an idea who is attentive right now. Just a couple of minutes for the poll to get over. All right, so let us see. Oh, 80% of them got it right. Rest 20, either you're not attentive or maybe you have any, some questions. So we have a Q&A here wherein you can put down your questions and we will take it up. All right, we have our mentor right here. So all the relevant questions would be taken up right here. All right, over to you, Swati.
Yes. Just excuse me for a moment, if that's okay.
Surely. Meanwhile, let us just see who is active here. Can we just have maybe a yes from the people who all are active in this particular session right now? You have the Q&A open. Let's see who all give me a heads up that they are awake and they are listening. Oh, wow. I can see only one responded saying that he's awake. Thank you, Ganesh, for acknowledging and responding to me. Hey guys, where are the others? Come on, let's see the Q&A getting flooded with people saying yes, they are attentive. And you always have this Q&A option to raise a question in regards to the session that is going on. Okay. We have another one saying yes. Thank you. Well, meanwhile, we have had 3 questions, in the Q&A, which has been taken up already. Right. So I hope that has answered your question, Vivek and Abhishek. I hope you're content with the answer that you received. All right, let's see what we can do right now. Let's see. Just give me a second. Okay, so we have questions which has been raised here. Ma'am, what to do to get placed in best companies like Google? I think that is taken up again. Then we have another question. I doesn't have any achievements in my CV, so how can I start to hunt for achievements? Okay, I mean, Mahendra, we are taking up this question and I hope that is answered for you. Yes. Feel free to put down the question. We have a little time wherein we can take it up right away. Mm-hmm.
Okay, I'm so sorry, guys. I'm back. Okay. So now we'll be talking about graph traversal algorithms. So sorry to keep you waiting. So the very important kind of algorithms which comes is, you might have heard of graph traversal algorithm, so being a type of non-linear data structure, traversing a graph. Traversing means to go to from one node to another node. That is what traversal means. So being a non-linear kind of structure, traversing a graph is quite tricky. So traversing a graph means going through and exploring each node, given there is a valid path through the edges to reach the node. So mainly, you might have heard of two terms called as BFS and, DFS. Breadth first and depth first, search algorithms. So breadth first search is a graph traversal algorithm that visits a graph node and explore its neighboring, or you could say the neighbors, before going on to any of its child nodes. Although you can start your traversal or traversing a graph from any selected node, the root node is usually the preferred. Root node means the first node. That's usually the preferred starting point. But you can start the traversal from any different point. Now, the next that you have is your depth first, you see. Now, your depth first is, this is the second major graph traversal algorithm, and it visits a graph node and explore its child nodes. Okay. So it explores its child nodes or branches before proceeding to the next node. That is what we call as a DFS, or a depth first search algorithm. So BFS is the recommended algorithm to find the paths between two nodes as quickly as possible, and especially the shortest path. The shortest path. Okay. DFS is mostly recommended when you want to visit every node in the graph, when you want to visit every other node in the graph. And both traversal algorithms, they work fine in most of the cases, but one might be simpler and more optimized than the other in selected, you could say, the scenarios. And there you have to make a choice whether you will be going with BFS or DFS. Now, a simple illustration can help you understand both the algorithms better over here. Think of the states of a country, like states in our country, right? UP, MP, types of things. Arunachal Pradesh, Himachal Pradesh, those states. Now, the states of a country as a graph, and try to check if two states, let's say X and Y, those are connected. So a DFS, it might go on a path almost around the country, the whole, our country that we have. So what it's going to do, it's going to go all around the country, and to almost without realizing early enough that Y is just two states away. So if X was here and Y was here, still it will be going through all the states, and then it will come and give you the result. Though it can be reached within just this particular distance, it was just, let's say it was just two states away from it. The advantage of BFS is that it maintains the closest, or you could say the closeness to the current role, or, the current node as much as possible before going to the next one. So it will find the connection between X and Y in a short time without having to explore the entire country, you see. So another major difference which comes is that between these two algorithms is in the way of, they are implemented in the code. So BFS, it's an iterative algorithm, and it makes use of a queue over there, while DFS, it's a recursive algorithm. It is a recursive algorithm, and BFS, it's an iterative. Okay, so here you make use of queue to implement it. DFS, it's a recursive, and you can leverage with the help of stacks. Okay, that is what the difference is. So let's see the pseudocode of BFS and DFS and how to implement it. So I'm pretty sure if you are into coding, you will be able to implement the pseudocode later on. So pseudocode is just, kind of the short code that later gets implemented into any of the programming language to achieve the result. So we have a function that will be creating a graph G and a graph node, let's say root. Okay. Now here you need a queue. So let's say you have a queue. Okay. Now the first time you mark the route as visited. So it's visited. That means we are going to keep it as true. Okay. Then you are going to add the route to the queue. Okay. You add the route to the queue. Then to add it, there is an enqueue operation. Okay, enqueue operation. So you just simply add it to the queue. Run a loop. It's an iterative process, I said. So you're going to run a loop and queue, until the time it is not empty. If it is not empty, you have to run a loop. Now what you have to do, you are going to remove the first element of the queue. Root means the first vertex. It doesn't means your tree. You have to start, from somewhere. So whatever is your starting point, you take it as root. You can even give some other name to it. Okay, you can give some other name. Give a start node. Give S node. Doesn't make a difference. It's just a name that you're giving. To understand, the starting point is called as root. Okay. The starting point is called your, root. Don't get confused with trees. Trees we are going to cover in another, class. So now while queue is not empty, you have to run a loop. Okay. Now you are going to remove the front element which is in your queue. You know, right? Queue. How it works. So you're going to remove the first element, the front one. So whatever is your current, let's say C, you have to dequeue it. So removal is dequeue. Okay. Dequeue that. So you are going to remove the front element. Run another for loop. Now this is all the neighbors in your current graph. G. Okay. That is all the neighbors which are in your current graph. That is what we are trying to implement. Now you are going to check if N not visited. Agar wo visited nahi hai, if you have not visited it, then you have to go to it, right? That is what you have to do. If you have to go on to it, that means you have to enqueue that operation and add it to the queue. And then put as N visited. Means once you have gone to that, node, you have to put it as a true. So just this is the whole algorithm, nothing much. You start from BFS, you take the graph, you take the starting node, then you take a queue in which you're going to add the nodes one by one. Okay. Once it is visited, if it is not visited, you have to visit that and put it as true. So you're going to check that. Okay. And then later you have to dequeue that as well. Remove it. Keep this process running until the whole queue is empty. Okay. That is what we do in BFS. Now in DFS or depth first search, what do we do? Again, we implement it with the help of a function. We create functions for it. It's simple. Again, it's not much. So you create a DFS function. There will be a graph and again a root node, a start node, whatever you want to say. Root. The base case, because it's a recursive algorithm. It's a recursive algorithm. Okay? So you need to have a base case. So base case is to stop. Why do we have base cases? To stop the recursion. So you're just checking if the root is null. Okay, if the root is null, then simply just return, do nothing. And you mark the root as visited for the first time. That means you put it as true. Run a loop next to reach all the vertices, all the nodes which are in the graph. So for that, you need a loop. Okay. And then what you have to do is It is a recursive algorithm. If n not visited, then run DFS again. Okay? That means this is the recursive call of it. This is only what algorithm or pseudocode of a DFS looks like. There are other, graph algorithm, like you have bidirectional graphs, you have topological sort, you might have heard of that. There is this Dijkstra's algorithm that you might have heard. Those are also there. Okay. So it's not that's only limiting to what you are seeing right now. There are different types of graph. You have finite graph. Finite means there are a defined, number of vertices and edges. Infinite graph, that means there are unlimited number of, vertices and edges. Next is your trivial graph. We have trivial, which is with only one vertex and therefore no edges over there. Simple means a simple is one which there is only one edge connecting a pair of vertices, like a railway track, connecting two different cities. That's example. You see, the examples are also being given over here. So simple is like a railway track. You go from one city to another. And now there is an edge. Multigraphs, you search for a location, like one example you said, Google Map. So there you search for a location in Google Map and it shows you multiple paths that you can take to reach from A to B. Do you know that? If I have to go from, Lucknow, let's say to Delhi, there is not just one way expressway. I can go from, different ways as well. I can take the Kanpur highway. That is what I'm saying. So that is a multi-graph example. You have a null graph. Okay. There are no edges connecting the vertices. That is your null graph. Complete graph. A vertex is adjacent to all of its other vertex. That is your complete graph, You have a vertex here, here, here. All the other vertices, they are adjacent to each other. This is a complete graph. There are many other graphs, like you have a regular graph. Okay. It's a regular graph. If every node of the graph is connected to the same number of vertices, that is your regular graph. Okay. Many different one, labeled one, direct, now there is a direct relation. You have directed graph arrows to show from where it is going to which part. That is your direct, Adjacency list, adjacency matrix, we've done those things. Fine. DFS, which is the traversal, we've done those things. Now comes, we have talked about quite a different real world applications of, graph, like we talked about social networking sites. We talked about connecting, with the help of Google Maps, where does it fit? The railway tracks, where does it fit? Let's talk about it a little more, to understand that it's not just limiting to theories itself, graph data structures. These data structures, they're not just limiting to the theories that we do. It's everywhere. We talked about that universe in itself is a graph, right? There are different nodes and edges, that connect those nodes together. So the real world application, you could say, if you look closely, the whole wide universe could be a graph in itself. We can think of the universe at the very start as a collection of abstract relations between abstract elements. So some researchers do have explanations about this theory, and it only seems logical, right? It's logical. The graph theory, it exists, it exists in the entire universe. And people, researchers, they have come up with the explanation to explain this concept, to explain this part from our perspective, from the universe perspective as well. But let's not go that deep into it right now because, we are not philosophers. So let's not just go too deep into that. And let's look at some real world applications that we can relate to. Social networks, we talked about social networks. This is one of the most basic application of graph. You see, a social graph, it illustrates connections among people and organization in a social network. Talk about LinkedIn, Facebook, Instagram, Snapchat, right? All those things, those come under this umbrella. Those are implemented with the help of graphs only. That's a real world implementation. Then the next is, again, talking about a web graph. Now, what's a web graph? Like, World Wide Web, the whole World Wide Web that we know. You go to a browser, type something, that is what your www. It's another huge graph data set where all the documents are connected to each other using what? Using hyperlinks, using DNS. So in this case, these hyperlinks, they can be considered as edges, that connects those, documents together. We talked about road navigation, road networks. So in computer science world, all navigation problems, they are fittingly termed as graph problems. All navigation problems, they fall under the umbrella of graph problems. So in a huge city where there are hundreds of roads and alleys and streets, graph guides you from point A to point B. You would have seen the roads, that are connected in the form of vertices and edges on many modern apps. You gave me an example of Google Map, like Uber. We see the map over there as well. On Ola also we see the map. So that is that. And not only that, but it also helps you find the shortest path, shortest possible route as well. That if I want to go from here till point B, what is the shortest path? What will be the time, that it will take? Even in the kilometers, it will give you that. The next is your product recommendation. Have you ever been to any e-commerce website? Flipkart, Amazon, Meesho, Myntra, Nykaa, and often, know what you want. Have you seen those things that, when you onto an e-commerce website, there you can see that how does this site know that this was the thing I was coming for? Or, you search for one thing and you go to another app, you'll see the recommendations of it. That is product recommendation. Now, how do these e-commerce websites, they know what product you want? How do they know that what product we want? So, and then they start recommending you all the alternatives or specific products. They use the graph data structure to establish those connections between what the users have liked in the past. There, your graph is again implemented. You might have heard of a new technology which is called as blockchain. In the recent years, blockchain has kind of erupted out of, and it's ruling currently. It's a technology which is ruling, and it is being deemed to be the future of all the transactions. Okay, in a distributed ledger that we know, the blocks over there, they act as vertices and they are all connected through edges again. That's how each user has the access to the required data, and all the transactions over there are transparent. Blockchain technology. When we talk about computer science, so graph, they define the flow of computation again. Control flow graphs we have, right? Which were, they act as a graphical representation again of computing during the execution of programs. They represent the network of communication. Again, any data organization that you want to do, again, you will be using graphs over there. OS, they also allocate the resources based on these graph structures to understand the state of the system. So each resource and process are represented over there as vertices and edges that connect the resources to the allocate processes. So that is where, in real world, this is all where you see graphs being, and many more examples of it. I might have missed a few, but there are many more examples of graph data structure, graph theory existing in the real world. Like you could say airline scheduling, the flow problems. There also your graph, it comes for directions in a map. We talked about that, shortest path. Graph coloring is another example, like solving some Sudoku problems. Okay, search engine optimization, search engine algorithms. The page rank, if you're aware of that, there also the graph is used. Social media marketing, again, that is your graph, you know. So there is a lot more. So we went over to a basic, of understanding what a graph is, how data structure, graph data structure it's actually made up of, or what are the different components, important things into a graph, and talking about how the data structure it fits well into the real world. Where do we see these data structures being implemented? Because this is the important question, and it's the most asked questions that I've got in my years of teaching. And not only in teaching, I also had this question, when we were the first time doing DSA, when I did DSA back in my college, I was like, where do we even use it? It's all so much to do. There are so many algorithms, but where does this exactly fit in? But when we go on this path, when we try and learn these things, we see that it starts getting clear to us. It starts coming back to us. Oh, yes, this is kind of a graph. Maybe at one point when I did DSA back in college in my second year, you might have asked me, where does this apply to? I would have told you, I don't know. Do we even use it? I see a question coming over here. There was this question, I think that was answered or what? How to become a software engineer by implementing DSA. So without DSA, without the knowledge of DSA, you'll be a programmer, you see. You will be a programmer, just a normal daily programmer, you could say, the mundane one, the one that will only be doing a task. I'll give you a task, you'll do the task. That's done. You are not expanding your knowledge. If you have DSA, the knowledge of DSA, you will be the best programmer around. You will be the best software engineer, So it's very important that you know how to implement DSA. The first thing is to get started with DSA, because in itself is a very big thing. Okay. It's, you start with it. You have to practice a lot. You have to get, acquainted with it, I would rather say. And then only you'll be able to make or, decision at, whenever you'll have a problem in hand and, you're working, you have something to design for. If you are very well versed with it, you'll be able to decide that now what kind of data structure I can use over here. So data structures is very important because you'll be handling data. If you are going mainstream into this line, if you are not someone who will be working with backends lot, the data more, you have to have the knowledge of DSA. You have to know how things work, and not only for all the backends or what I'm talking about, it's for all of them. It's a basic thing that any programmer should know. If you're not aware of it, I might say that not a good enough programmer, not a good enough engineer, because this is the basic requirement. You go to any big companies, the top product-based companies that you have. Another question, what to do to get placed in best companies? So best companies, they have these DSA rounds alone, alone they have these DSA rounds. No other question. What is for loop? No, they will not ask. They will give you these kinds of problems. They'll give you a problem which will be entirely based on data structures, and you have to solve that. So to get into best top, based product companies, I remember taking a class on that as well, a live lecture, where we talked about how to get placed into these best top, not even the, the best companies, I would say now this is a requirement. You'll have DSA rounds. There is a DSA round that you have to clear. They'll give you questions based on DSA. They'll give on graph, trees, arrays. You think array is very simple, but when you have a question in front of you based on an array, sometimes people, they are not able to implement that. So a lot of practice is what that will get you placed. A good guidance will get you placed. Someone, who can actually tell you that how to proceed on that path, will get you placed. So I doesn't have any achievement in my CV. How can I start to hunting for achievement? I mean, like hunting for achievement, the question is a little vague. Hunting for achievement is nothing. You have to achieve something. So you'll start with something. So to achieve something, start with it. Start maybe if your CV is plain old, you're not aware of much of the concept. Sometimes we think, Arey, we know Python. But when we actually have to do Python, have to implement, we are not able. So that means you still have to do Python. You still have to do Java if you're not able to implement simple programs. We're not able to build projects around it. Just writing those things on your CV will not help you. Basically, the good amount of guidance, someone, and your determination to practice again and again. The only thing that matters to be a good programmer is a good hand and, at the back of your head, and practice, the attitude to practice again and again. The more you are going to practice, the more questions you are going to do, the more scenarios you are going to solve, the better you will be. Yes, I have another question, that you have a degree which is from a non-IT background, BWalk data science. Okay, but so you can get a job. Yes, you can get a job. I let my counselors get in touch with you. Yes, you can get a good, decent job. Okay, again, the one thing is practice. Your hard work is what is required everywhere. Okay, so I am done with the session. Ruby, I would like you to pitch in.
So I think we have answered all the questions that were there in Q&A. We just have a quick polls coming up so that we understand, who all are, interested in knowing how they can, upskill themselves and what kind of opportunities would be there in the market open for them after they upskill. So we will just, okay, here is the poll. Are you interested to know more about our full stack development program? You have two choices here. One is yes, one is a no. All right, I would like to inform you all that, as discussed earlier, that we are an upskilling platform that helps you, get skilled as per the current industry standards, as per the employer requirements. And we do have 100% job guaranteed program, which comes with various payment options like pay after placements and upfront payments as well. So you have a lot of flexibility in that as well. So in case if you're interested to know more about it, and if you want a little of career guidance, kindly let us know so that me or my team, get back to you. We give you a call and we explain you how we can actually help you get to your goal. If we get a yes, we will connect with you. Just few seconds for this poll to end. All right. Thank you so much for that. Also, the last thing I would want to, put it across is that we have, as mentioned, we have 100% job guarantee programs, which comes with the average package of at least 10 to 12 lakhs. That's the kind of package that we have provided in the past to a fresher, the, full stack developer fresher. So that's the kind of opportunity would be open for you. So kindly, if you put in a yes, kindly expect a call from us. We'll get back to you soon. And lastly, I don't think we have any questions here, so we will move towards ending this session. Thank you so very much for being a part of it this Saturday morning. We look forward to see you soon, the coming Guru class. Thank you so much.